Talk is about reversing Android application. I'm the last wall between you and the beer, so I apologize for that and also for my French English. But I'm going to explain you why and how we reverse application at Google by giving you some example. So first, I'm not a developer, so this is my very, very simplified view of developing an application. Please don't take offense of that. So the first step is to write code in Java, Kotlin, C, or C++, whatever you want. And then you generate the APK, and obviously you want your application to be used by users, so you have to publish it. My job, this is a very, again, simplified view of the workflow of a reverse engineer, is I get the APK, I spend a lot of time to understand the code, get the logic, understand what the application is doing, and then I have to make a decision. Does this application meet our threshold? I will explain right after what is our threshold here. So, as you can see, a developer and a reverser are doing totally opposite things. The legit question here is why does Google need to reverse application? Simple answer, it's all about security. We want that every Android phone to be a safe environment for the user, and I mean every user feel confident by using the Android smartphone for whatever they want, banking, communicating, using social media, whatever they want. And the way it can be achieved is by enable Google Play Protect on your smartphone. The first option, I think, is enabled by default, and the second one, I will explain you later why it's useful for us. But please enable the two. Okay, this is the screenshot at the top is what we try to achieve. I mean, having a safe environment where the user can execute all the application he has without fear. And the screenshot at the bottom shows that a problem has been detected by Google Play Protect, and Google Play Protect is handling it. So on the left, the application is not safe, but not too much, so the user can still execute it if he wants to. Otherwise, he has the option to uninstall it. And on the right, the application is not safe at all, and it will be removed, and no other options are possible. At Google, we define PHA, which stands for potentially harmful application, which is our name for malware. So PHA are applications that could put users, user data, and devices at risk. We have, for example, spyware. Basically, those are applications that gather your personal information and send them to a third party server. We have also phishing applications that try to act like, for example, Facebook or WhatsApp, steal your credential, again, exfiltrate them. We have also billing fraud, that applications that are able to send premium SMS, so you will be taxed for that. And obviously we have applications that are able to root your phone, which is not allowed. And you can see more categories on the website above. This is for all applications. We have also what we call mobile unwanted software, like a MUSE, and it is only for applications that are living in a Google Play Store. So these apps are strictly not malware, but they are harmful to the software ecosystem. A MUSE application impersonates other apps or collects at least one of the following without user content. It could be device phone number, primary email address, information about installed application, information about third-party accounts. In fact, all of this information are able to fingerprint a user, and we don't allow that. Okay, as I told you before, the first step of a reverse engineer is to get the application. At Google, we have 3 ways to fetch application. The first one, the simple one, is the Google Play. Google Play Store is our main database. We have access to all applications published in our store. The second one is quite new. Actually, in 2017, we had begun scanning what we call pre-installed PHA across many software builds. I mean, when OEM wants to sell a new smartphone with Google services inside, it must give us the system image in order to pass a lot of tests. And this is where we can grab the application on those system images. And the last opportunity we have is to get application from alternative stores. I don't think we are allowed to crawl this store, but when a user installs an application from the store, there's also many more stores, or gave an application and uploaded through ADB. And it enables the second option, improve harmful app detection. And then, if we don't know the digest of the application, we upload it to our server, and the application will be scanned like the others. So now we have the application. The next step is to analyze the application to give our final verdict. We are able to scan up to 500K applications per day, and obviously we don't do all that by hand. We have machine learning algorithm, other signature tools that work for us, and if they are able to conclude, then the application is approved or rejected. But when they cannot decide, we need to review them manually, and that's what I'm going to show you. Okay, now let's enter into my world. I will show an introduction of reverse and Android application with public tool and some problem we are facing. Again, I'm not a developer, so I made a very next generation application that can collect the stored SMS on your phone, and when you hit the fancy button, it extracts all of the SMS and exfiltrates them to a third-party server, and there's also the ability that when the phone reboots, it does the same thing. Okay, so this is my application, which obviously is a PHA because it steals your SMS messages without your consent. I mean, by consent is not just the title in the button. Okay, is an application that does this kind of thing has to show a very big activity and explain what is doing with all your information, where they are uploaded, things like that. Okay, so it's a spyware for us, but let's analyze it. This is my code, okay? It's very simple. I have hard-coded string inside in order to debug things. This is my activity. When I push the button, it starts an intent service. Again, the boot receiver completed, which when trigger this intent, it starts my SMS backup services. And this is my backup, SMS backup service. Nothing very complicated inside. It checks the network. If the network is available, it gathers SMS and sends it. And as you can see, I have hard-coded my server URL, and I will show you later what is it. So this is my Java code. And now when you hit the button Build your APK, you get a file with the APK extension, which is basically a zip file. Okay, so I can use the command line unzip in order to unzip all the content. We have the manifest file, which is very useful for me because it shows me the entry point of the application, what activity are used, what receivers are declared, what services are declared to. We have the dex files, which are the Dalvik bytecode, which is the code that runs an application. You have also the lib directory, where native libraries are living. And we also the assets directory where other files that may be needed by your application are going to. And maybe some developer, at least malware developer, try to be clever by hiding native library, not in the lib directory, but in the asset library. Okay, why not? So I have my application and I want to analyze it. The first step is to disassemble this file, the DEX file, which contains the code, into a more readable file format. So I need to disassemble the bytecode into a Smalley assembly, which is kind of more readable. As you can see, this is a code I get when I disassemble the DEX files. We have all information inside, my hard-coded string inside, the name of the function, the code organization is quite the same, but in a different format. And because I'm a lazy reverse engineer, I consider reading Java code is faster than reading Smalley code. So I use what is called a decompiling tool. Basically disassemble the DEX file into a Smalley assembly file, and then from this Smalley it decompile it in order to get the Java code. This is a non-exhaustive list of tools you can use. The three first are free and open source, and the last one you need to pay a license in order to use it. Okay, when I hit the button decompile, I use Jeb for this demonstration. I load my APK file, and this is the result I have. On your left, you have, like in Android Studio, the code organization, the same name of file, thing like that. And we have also all hard-coded string, and as you can see, it's far more readable than Smalley assembly language. It's Java. It's better for me. But when a malware author doesn't want to show me the hard-coded string, because it's kind of easy to use the search function, they use what we call string obfuscation. The basic one is they use the base 64 encoding, and as you can see, you will get also an ASCII string, but less readable, but you can script this easily. In order to not be searchable, they use a trick, which is very annoying, but we can do it. They convert the string into an array of bytes, and so I'm not able to search anything. They also use encryption algorithm, whatever they are, the simple XOR or the AES 266. I only consider those algorithm as obfuscation algorithm and not encryption, because at a point in execution of my application, the string must be decoded, disobfuscated. So I have my decryption algorithm, I have the encrypted data, and I also have the key. So if I have the three, I can get easily the decrypted thing. So whatever they use, symmetric algorithm, encryption symmetric algorithm, or just encoding, it does the same for me, just string obfuscation. And some obfuscation software rename everything, the package name, the class name, the function name, the variable name. They also are able to use encryption mechanism on hard-coded string. And when you face this kind of application, you know the next few hours of your day are totally ruined, and you only do refactor and search and replace option in your tool. So yes, we lose time, but at the end we will get the logic and we get the application too. Another way to obfuscate code is to put it into a native library. Actually, it's not an obfuscation, but since it's easier to decompile DEX file into Java rather than decompile native library into C or C++ code, most people consider it a way to obfuscate data. So this is, again, a very simplified view. I've got my APK, and inside I have my native lib.so, which declare, a function which I can call in the Java code with do native bad things, and I put a pointer of my function into my native library. And in my Java code, I declare a public static native void the name I declare in my library. So when I see this kind of code, I know I have to dig into the dynamic library. And yes, for this example, on create, when the service is created, it loads my native library, and then it executes the function natively. So yes, it's not obfuscation, but it adds some step for me to analyze the application. When everything is combined, you lose a lot of time. This is a real example I analyzed months ago. So I have my APK. Inside I've got dynamic library with some file into the assets. Okay, let's see what they are doing together. First, as you can see here, three native functions are declared, should be declared into my native library. And when the service is created, it loads my library, and then it calls a function into my native library too. Yes, this is. Now I try to scare you. Where are my tools? Yes, this is one of my favorite tools. It's named IDA. It's like the same like JEB or JEDEX. It turns my native library, my native code into a more readable code like C or C++. And when my Java code call the load library function, the main entry point is a GNE onload function. This is the very first instruction that are executed. And this is not obvious yet, but here, from line 18 to line 26, this is my array of GNE native method, which is here. And as we can see previously, I need a string, which is the name of my function, is prototypes, and then a pointer into my C code. So now I don't have any function name here. Okay, this is definitely not a function name. This is neither prototype, which is a string, but when you analyze this function, at least this one, okay, and this one, you have this code which turned to be the decryption algorithm for my string. So this is a Python code that can do the same thing, which decrypt my string. So I developed a script, and in order to get my life far more simpler, I put this one and the magic. Okay, this is the equivalent of, this is the decryption result of those byte array, and this is a service Taylor underscore A, which is one of my three function decrypted. So to go back to my presentation, it loads the native library, and then it decrypts its own string. So the string are obfuscated into the APK. They are also obfuscated into my native library. So yes, it took me a few minutes to decrypt them. And then when the APK and the native library gets their own code decrypted. They can do the next step, which is take those files into the assets directory and again decrypt them. So if you, the decryption algorithm is quite simple. You've just have the XOR operation, and the key is derived from the file name. So nothing very complicated, but it's always annoying to do that. Yes, and when the assets file are decrypted, you got the MLF executable, which is only here just to recall the service into the APK, and this kind of persistence mechanism. And the other file in the asset is the first stage. It's another APK which is loaded, and this APK is also obfuscated. You know, he rename every class, every function, so it's really annoying, at least, to analyze it. But by any chance, the developer left some comment, so it saved me sometimes. Okay, and after a few stages, at the end I've got an HTTP request which download the final payload onto a third-party server and get it, DEX class load it, and then at the end it was a routing exploit, which so the application is obviously a PHA because it tried to to exploit a vulnerability in order to root your phone. It took me about 2 days to get all of things together, so I lost a lot of time to analyze it, but now I was able to flag thousands of Android applications, hundreds of thousands of applications. And this is what I have to do when I want to analyze statically an application, but when things are not, when static analysis is not enough, maybe because the application is too heavily obfuscated or the code base is simply too big and complex to quickly isolate the routines you're interested into, you need to go dynamic. And dynamic analysis simply means that you will execute the application into an emulator on a real device in order to understand what is happening. So you can able to log all the events on your device if you recompile the AOSP environment in order to log everything. You can obviously inject your own root certificate in order to intercept and decrypt every network traffic. So you can do this quite easily. And you can also take the application, make it debuggable. You have to unpack it, add the Android debuggable equal to true in your manifest, resign it and execute it, and use one of your favorite debugger, which Android Studio is not, Android Studio is quite good to do that. We have also a very powerful tool named Frida. It's a dynamic code instrumentation toolkit. It allows you to inject JavaScript into your application, and with that you are able to hook every function, call function. For example, this is an example of when an application wants to load a DEX file. Usually use a loadDex function, and this function is a hook, so before calling the real function, I put just some line of code in order to get the file is trying to load, save it into my own repository, and I will try to analyze later. Because some malware authors are very clever, they try to load something, and when the code is loaded, they deleted it just after. So when you execute the application, a few minutes after, you want to try what DEX file have been loaded, and you don't have it. So this is a way to get everything. And obviously, we do some dynamic analysis, but malware developers use anti-dynamic analysis tricks. They are able to call the function isDebugger connected in order to know if, for example, Android Studio is connected to your application. If that, they don't do anything, or they do something else. They're also able to check what process are running on your devices, and if they see one of the famous debugger process name, they can also kill themselves or do another thing. And also something we see a lot, if when you execute a function, it takes I don't know, a few milliseconds, and so malware author put a timestamp just before the interesting part, after the interesting part, and compute the difference. If this difference is very small, it means that nobody is trying to analyze nobody is trying to trace application instruction, and if the difference of time is bigger than a certain value, then they can act differently. They're also trying to detect emulation, because when you run your application into an Android emulator, some few things are not coded into the emulator. Like, okay, the battery never changed, so they're able to check the register to this event, and if they don't have any trigger, if they don't receive this event, they do something else, thing like that. We have also the check sensors value. If the phone doesn't move, the GPS is not turned on, something like that, the application won't run, or it does something else. So in conclusion, yes, don't be afraid to reverse application. It's fun, actually. I think it's fun. If you want to go into that, start slowly with some CTF, capture the flag, and then you can also reverse your own application. And after, when you feel confident, you can give a try to well-known PHA, where you can find a lot of analysis on internet. And finally, you can apply, because we are hiring. If you want to give a try, please. And obviously, malware authors are very creative. It's easy to catch script kiddies PHA, like I coded for my SMS backup application. But some of them are very creative. It took us a long time to track them, and it's difficult to track, to catch. They are quite difficult to analyze. And sometimes we know that something is happening, but as we don't have any evidence, we can flag them as a PHA. So we are trying to developing a lot of techniques to, yes, make them, make their life harder. And I will finish with this slide. It turned out that we do our job pretty well by taking a look at the number, but obviously we continue the battle in order to make the Android ecosystem a safer place. So thank you for your attention. If you have any questions.